Good afternoon. So in today's lesson, I want to go over another example of a wave equation involving the general solution in the format we derived last time. It's basically the only example that we deal with which doesn't use a series format of the solution. But I want to take my time in this example that I'm going to show you today to give you yet another motivation why the series solutions format is necessary in many cases, because this general solution, it might not be useful if you add on top of the PDE, on top of the equation itself, other conditions. So let's actually summarize briefly what we dealt with or what we obtained last time. So we show that just by solving via substitution the partial differential itself, the wave equation in one dimension, we show that the general solution looks like this summation of what we call the traveling waves, right? So two functions phi and psi evaluated at x plus at, x minus at. Now remember, if this is just the PDE itself, normally the idea is to actually figure out what these functions are, phi and psi, once we impose the boundary conditions, because without the boundary conditions, again, these functions could be any function, and that might be nice, but that's not really useful. The idea is to match the solution with boundary conditions or initial conditions, which will allow us to actually determine these unknown functions phi and psi. So these are functions of a single variable. It's important to point this out, right? So phi of x, psi of x, or any variable you want to replace x with. So these are functions of a single variable, except that in the solution, they are evaluated, each of them, at x plus at and x minus at respectively, the other one at x minus at. We also showed in the previous lecture that if we impose just two particular initial conditions, so still no boundary conditions, namely the initial velocity 0, and the initial displacement given by a known function f of x, then we show that the solution is given by f of x plus at, f of x minus at. So in other words, the traveling waves are given by the function itself, the one that gave you the initial displacement. To obtain the solution of the wave equation, all we have to do is to evaluate this function at x plus at and x minus at and add the two. Sorry, this is over 2. I forgot the semi-sum, right? So the semi-sum of these functions. Now, this is appropriate on its own, this problem, if, and this is the key thing for this presentation today, if the wire is infinite in length. So that means the domain for x is all reals. Right, so no restrictions on the length of the string or the vibrating string. That's why we don't have any other boundary conditions. So what happens if you do have some boundary conditions? So this time I'm gonna make it still kind of infinite wire, so but only on one end of it. And this is actually similar to a homework problem. I'm gonna basically go over a simplified version. But imagine that what you have here is basically a wire or a vibrating string that is infinite in length, but one end can, let's see, can slide along a fixed vertical pole. So in the sense that it's still infinite in length, but there is a boundary at one of the endpoint, at one point of this wire. So just to illustrate what we're talking about here, let's say the vertical pole that is fixed to the ground corresponds to the y-axis, and you have like a little ring here from which the wire is attached, and this ring can move up and down along the vertical pole, which is again denoted by or represented by the y-axis. So for example, if you this ring could be here, and then the wire maybe hangs like this. But anyway, the end point of the wire can move up or down. In this configuration, the dependent variable, which denotes the displacement of the vibrating string, doesn't make sense to make it defined for all x. So in this case, x is strictly greater than 0, or greater than or equal to 0. That doesn't matter as much, right? What happened at 0. So just positive x, not the whole x-axis. And let's say we're looking in forward time, what happens in the future. So that means t is greater than 0. But the stuff that will make it a little bit slightly trickier to solve as compared to the previous case is the fact that, again, the domain is not all x. And this is crucial, you'll see once you go over the process of actually determining these traveling waves. So let's come up with a boundary value problem involving this configuration, and let's try to find the actual solution by, like I said, actually determining these phi and psi. So let's say, again, to make it as simple as possible, let's say the boundary value problem, again, is the wave equation. And let's say the initial displacement is 0. Let's say the initial velocity is 0. So partial t of x and 0 is 0. And let's say at time t, for all time t, the left endpoint, y of 0t, is kept at height 2. Doesn't matter actually what the value is. Let's say 2. So y of 0t equals 2. And then the question is to find the solution of this boundary value problem. Now, again, let's imagine what happens in the beginning and then throughout the process. All right, so you have this fixed pole here. When t equals 0, initially, the wire lays down along the x-axis. Again, infinite in length. It goes indefinitely to the right-hand side, attached to this ring. And then as soon as we start the chronometer, in that fraction of a second, this ring jumps all the way up to position 2. Right? Y of 0 equals 2 at that instant. So really imagine the movement. The wire is in the equilibrium position, laying down along, over the ground. And then as soon as you start the chronometer, right, and you measure the time, this moves immediately upward, this ring, to the position 2. So if you think carefully what is going to happen here with this movement, you should have basically some sort of upward movement of the entire ring that keeps on moving to the right like that. Because remember, there is nothing to snap back the ring from right to left, because the ring is, the wire, because the wire is still infinite. But this jerk movement from 0 to 2 will raise, obviously, the wire up to 2 level, and then this wave is going to travel to the right. So the way the solution should look like, if I were to solve it, it should be some sort of a non-zero value to indicate the displacement. And at some point in time, it should still be 0, as you move to the right-hand side. Because again, it's infinite in length, so from a certain point, the wire is still lying to the ground, because the effect of this jerk on the left didn't arrive to that point yet. So really like a wave moving to the right-hand side up to level 2. So like that, let's sketch a couple of, right? This is the type of movement you should see. So again, at a certain point in time, the displacement should still be 0. So this looks like a piecewise defined function. So I'm anticipating already that the solution is not going to be just one formula for the function. And let's see how mathematically this ends up being the case. So starting from scratch, again, we know that the general solution is in terms of these two unknown functions. And now let's impose the initial conditions first. So y of x0 is, so t is equal to 0. So that's phi of x plus psi of x. And this should be equal to 0. We also need the partial derivative with respect to t. So yt of xt, using the chain rule, that's going to be phi prime of x plus at times a, and then plus psi prime of x minus at times minus a. All right, so let's keep this in mind. And now let's replace t with 0. And this becomes a times phi prime of x minus a times psi prime of x. And this should be also 0 because we have initial velocity 0. We can cancel a. And together with the previous condition, we have that phi of x plus psi of x is equal to 0. Phi prime of x plus psi prime of x, or minus psi prime of x, is equal to 0 as well. Now the second condition states that the derivative of the difference of phi and psi is 0, which means that phi of x minus psi of x is equal to some constant c. Now keep in mind, everything I wrote so far is just for x greater than 0. This is the stuff that people may miss here if you don't remember your restrictions in the problem, right? The wire is not defined for x or minus infinity infinity, but for x greater than 0 only. And this will be a problem because take a look at this again to the general solution. So that's the key thing. Even though x is greater than 0, for some combinations of x and t, so although both x and t are positive, for some combination of x and t, x minus at can be negative. And therefore the question is, once you find psi for positive arguments, you still need to find a formula for psi evaluated at negative arguments. So far basically x is positive. I didn't basically touch what phi or psi is if x is negative. So let's finish up actually finding phi and psi if x is positive. And we could do this just like in the previous lecture by combining these two equations and just solving for phi and psi. So if I add the two together, I have 2 phi of x equals, excuse me, this is going to be a constant c, equals a constant c. So phi of x is equal to c over 2. Psi of x is c minus phi of x. No, phi of x minus c. C over 2 minus c, which is minus c over 2. All right, again, this is just for x positive, And we're going to have to continue on the second page, but let's summarize. So phi of x is some constant over 2, psi of x is the opposite of that constant, just for x greater than 0. We still need to figure out what phi is for a negative argument. Notice there is no problem with phi. In the solution, x plus at is always positive. So phi of x plus at in the actual solution is still c over 2 for any x and t. Any combination of x and t, both positive, x plus at is positive, so that's going to be some constant. But for the second part of the solution, we need to find what that is in case the argument is negative. So let's stay tuned for the second page. All right, so once again, the general solution is this. We just established that phi of x is a constant, psi of minus x is the opposite of that constant if the argument of this function is greater than 0. Therefore, the solution itself is going to be c over 2 minus c over 2 equals 0 if x plus at is greater than 0, which is always the case, right? Because we are under the assumption x greater than 0, t greater than 0, and x minus at greater than 0, which is not always the case. So that's just basically 1/2 half piece of the solution. Now we need to figure out what is psi of x minus at if x minus at is negative. In other words, we need psi of x if x is negative. So basically we need a formula for a psi of x if x is negative. So in this particular case, this comes from the boundary condition. So remember, there is still a boundary condition which resulted from moving that ring upward 2 units and it's kept there, right? So that means the condition was y of 0t equals 2. So now plugging in this into the general solution, this means we have phi of 0 plus at. Now you replace x with 0 plus psi of 0 minus at, and this should be 2. So notice again that since t is greater than 0, a is greater than 0, phi of at is again that constant. And if you get this by itself, we have that psi of minus at equals 2 minus c over 2. Okay, so basically now to find a formula for a negative argument, basically you can replace this with x essentially, right? I mean, you can make a substitution. That means like replacing t with x over a, and that gives you a formula for the negative argument. Now, since the right hand side is a constant, there is nothing to replace on the right hand side, although the boundary condition can depend on t itself, as in the problem in the homework, in which case you'll have to make these substitutions everywhere in this equality. But the point is in this particular case, from the boundary conditions, we can actually get what psi at a negative argument is. So psi of minus x is 2 minus c over 2 if x is positive. So that means you have a psi of a negative value. You could also, you can make this notation more flexible. I mean, you could say psi of x is equal to 2 minus c over 2 for x negative. So you can bring the negative sign, you know, inside a t, for example. In that case, you would replace t with minus x over a. But that's just semantics. Whether you call x a negative argument, or if you want to keep x positive, then you keep the minus out. Bottom line is that in the actual formula for the solution, you're going to need to write what psi is for a negative argument. So in other words, if you write the full solution again, and here for x minus at, if I pull the minus out, you can replace this with the new x and then write down what psi of minus x is. Again, in this case, it's going to be just a constant, 2 minus c over 2. So this will be basically c over 2 and then plus 2 minus c over 2. Again, if the argument is negative. So in other words, if x minus at is negative, or t greater than x over a, if you write this in terms of t, however you prefer. So when we put everything together, the general solution of the PDE, of the boundary value problem, is 0 if x minus at is positive, and 2 if x minus at is negative. In terms of conditions for time, this could be written as t less than x over a, x minus at negative t greater than, and 2 if t is greater than x over a. So at some point later is equal to 2. All right. me make sure actually I wrote these conditions carefully. So f, say, of x minus at, it's 2 minus c over 2 if x minus at is negative, and then add it to 2. Yes, okay. All right, so in the actual problem that you have assigned, you're gonna have basically the same thing except the right hand side. I mean the condition on the boundary y of 0 t is not just a constant number, but it's a function of t. So in other words, that ring kind of goes up and down that pole in accordance to the value of this function with respect to the time t. So the same idea, except that when you make that substitution, t with x over a, make sure you make it also into the function itself. So in conclusion, if you add other boundary conditions, things can be much more difficult in terms of actually determining these functions phi and psi. That's why we prefer later on to use the series representation, which will be the main topic for the class. So that's it for today.